So the agenda for today is just to give a brief and for today is to give a brief overview of polynomials in general. So the different types of polynomials and how to calculate the degree and stuff like that. Then we will now focus on just univariate polynomials, then explain the evaluation, interpolation, and then we'll start implementations. Does that make sense? How many of you are familiar with Rust? That was the prerequisite though. You guys are not confident with Rust? Okay. So it might be slower, but we'll do it. Okay? Alright. Wow. Okay, so polynomials are made up of monomials. Oh, sure. So I'll send this to everybody eventually. The main thing is just to get the idea. Alright? Is it clear now? Okay. So polynomials are made up of monomials. Right? A polynomial is just a sum of monomials. So you have a monomial plus another monomial plus another monomial. That's all a polynomial is. Okay? So first of all, describe what a monomial is, and then we'll show how you build polynomials out of monomials. So a monomial is just the product of numbers and variables. It's as simple as that. Okay? So you have numbers, so they can have like 2 times 3. Then you have variables, which could be A, B. Right? So 2 times 3 will always compress down to a single number, right? So when you multiply multiple numbers, it will compress down to just one number, right? So 2 times 3 is basically 6. So a monomial is just like an optional number and an optional set of variables, yes. Then the variables also can have exponents, right? So you can do 2 times a, which will compress down to 2a squared, all right? But monomials can only have whole number exponents, right? Yes, exponents. So you can't have a raised to the power or b raised to, for example, b raised to the power of minus 2, right? Because of this is not a positive exponent. Then this is not a monomial either. Do you know why? I already wrote the answer there. But the reason why this is not a monomial is because of there's a sum there. So these 2 monomials making up one polynomial. Then this is also not a monomial because of you have a variable that has a fractional exponent and you only need positive whole number exponents. Does it make sense so far? Yes. So monomials are pretty easy. So the question now is that how do you compute the degree of a monomial? So the degree of a monomial is the sum of all the exponents. I don't know if that makes sense. So this a now, the degree is 1, right? Because this is technically a to the power of 1, right? So it's just 1. Then 5a squared, only one exponent there, which is 2, right? So that the degree of this monomial is 2. Then a cubed b squared, 3, 2, right? So the degree is 5. Then a cubed, 4a cubed, b, c, 4. That's 3 plus 1 plus 4. Does that make sense? Okay. So let's just do some exercises. So this is important for why we care about the degrees, because of when you're computing the security. So like a ZK system now, you want to determine, okay, how secure is this? Usually, for some protocols, you need to do an analysis on the degree. Okay, so that's why it's important to know how to compute the degree of monomials. All right. So what's the degree of this? So anybody can just shout out the answer. And if you have shouted the answer correctly, then just don't talk again. 4. No worries. Then what's up? Yeah, the degree is 4. You can come and learn too. What is the degree of this? 6. What is the degree of this? Okay, cool. What is this? 9. Okay. So calculating the degree of monomial is clear, right? Right? You are late. Sorry. We can't go back. But the idea, a monomial is just a product of a number and variables, right? So 5a squared, then 4a cubed, b, c. So the degree is just the sum of the exponents, right? So in this case now, the exponent is the power of a variable. So all the exponents. So if there's no exponent, then the exponent is 1, right? So here the degree is 1 because it's just a. And then here the degree is 2 because it's a squared. Here the degree is 5 because there are 2 exponents, 3 and 2. And here the degree is 3 plus 1 plus 4. Does that make sense? Which is 8. Cool? Alright. So there are different types of monomials now, which also mean that there are different types of polynomials. So a polynomial that is built up of a certain type of monomial would inherit the name of that monomial. So the first one we're looking at is the univariate monomial. So a univariate monomial is basically a monomial that has just a single variable. Okay? So you know how we have like products of multiple variables or one or more variables. So when it's just one, that's what they call a univariate polynomial. So the variate is like variable and uni is like one. So univariate. So one variable. So these are examples. A, 5a squared, 2x, 45y cubed. Does that make sense? It's very simple. This is a simple part. So a multivariate monomial is now when you have more than one. Okay? And you can technically think of a univariate monomial as also a multivariate monomial, kind of. Because multivariate is more like one or more, kind of, right? But for our cases, we'll just make a distinction that, univariate 1, then multivariate 2 and above. So these are examples. This one has a and b, this one has x and y, and this one has z. Does that make sense? So then a polynomial is just the sum of, so you can have 1, 2, 3. So every monomial is technically a polynomial, right? Does that make sense? Monomial is like it's like one or more. So if it's just one, it's still technically a polynomial, but it's also a monomial. So you can make it more, you can be more precise with your statements. You said? Yeah, exactly. So so each monomial in the polynomial is also called a term. It's called a term. So if someone says that the first term, you can just know that okay, it's the first monomial. But these are very simple. The more interesting thing here is now the degree of the. Okay, let me just give it. So like a polynomial that has just one term is a monomial. This is what I was talking about. That a monomial is also a polynomial. If it has 2 terms, it's a binomial. I don't know if you remember secondary school where we're talking about binomials. Then 3 terms, trinomial. But everything is just called polynomials. The reason for this specifics is when you're trying to communicate with someone and you want to like exchange an idea quickly, right? So you want to be precise and say that okay, I'm talking about a polynomial, but this polynomial has just one term, or it has just 2 terms. So that's the reason for this language. Does that make sense?
Sorry, so if we have 4a plus 5b plus 6c, do we now call that a polynomial because it has 3 terms?
You call it a trinomial. You call it a trinomial because it has 3 terms, but it's also a polynomial. Does that make sense? So like saying a trinomial, you're basically saying that this is a polynomial that has 3 terms. It's more precise. A polynomial is just this is a polynomial. But if you want to give more information about the nature of the polynomial, then you can now use terms like this. Does that make sense? Okay, cool. So polynomial is just a sum of monomials. And we already know there are different types of monomials. So depending on the type of monomial that you're summing, that will determine the type of polynomial that one is using. So in the first one we're looking at is the univariate polynomial. So the univariate polynomial is basically a polynomial that is built up of univariate monomials, right? Not necessarily univariate monomials, but like they are all univariate monomials, and they all have the same variable. There are two conditions, right? So all the monomials must have just one variable, and all the variables must be the same. Does that make sense? So in this case, if you look at this is an example of a univariate polynomial. Technically, it's just a univariate monomial, but a polynomial is a monomial, so it's fine. But in this case now, we have what you call like a polynomial, technically, because of the sum. But if you look at the variables, they're all a's. Here, there's an imaginary variable, which is like technically like a raised to the power of 0. Right. Because anything raised to the power of 0 is 1. So it's to collapse down to 8. So technically there's an invisible a raised to the power of 0 there. No, I even wrote it down there, I forgot. So this is what I wrote there. It can be seen as 8a raised to the power of 0. So what's the degree? How do you compute the degree of a polynomial? So the degree is just the highest monomial degree. So you know how to compute the degree of a monomial, which is the sum of each. So all you need to do is just go through each monomial and say, okay, what's your degree? What's your degree? What's your degree? Then you say the polynomial degree is the highest one you found. Cool? So we'll go through some examples now just to... so in this case now, what will be the degree? Exactly, because that a cube is the highest one. So let's now go back to this and just like play with this a bit. So you can have 2x squared plus 3x cubed plus 4x plus 8x. So what's the degree of this? 10. Yeah. So the univariate degree computation is not crazy. There's no need to do too much here. I think that one is clear. So now the multivariate polynomial. In this case, the monomials now are multivariate monomials, right? Like the entire polynomial is now using more than just one variable. So it's not just a all true. It could be a and b, c, yeah, any combination of that. So these are examples, like x squared y cubed. Where's my mouse? Yeah. So x squared y cubed, for example, is multivariate because we have two variables. So multi, more than one, variate, variable, two variables. So this is the function signature for this. Just the variables, the distinct variables that are there. Alright. Like that was also the same thing we did here. There was only one distinct variable. So by looking at the function signature, you can technically know the type. Yeah. So if function signature just has one, then you know that it is univariate. And if it has more than one, you know it's multivariate. So the degree of this, now let's play with the degree. So this one has just one monomial, so we'll instantly inherit that, right? Because that will technically be the highest. And the degree of a monomial is just the sum, right? So 2 plus 3, that's 5. So that's the degree of the polynomial. Then in this case, we have two terms now. The degree of the first monomial is what? The degree of the second one is what? So which one? What will be the degree of the polynomial? Exactly. Then likewise, what's the degree of this? So what will be the degree? Yes. So it inherits that. Is it clear to everyone? Yeah. Okay. Cool. So the degree computation is basically the same. Now this is a very interesting polynomial. This is one that we're going to be spending most of our time because of the protocols that we're going to be using. Use this a lot, and there's a specific reason why. But we'll get to that. So this is called a multilinear polynomial. It is a special type of a multivariate polynomial in the sense that it is still multivariate, but it has a special property in terms of the degree. So the degree of every variable must be 1. Variable, not term, not monomial. Variable. So that means you're never going to say a variable that is a square. You only see a. And you're never going to say a variable that is b square or c square or cube. There's no power in the entire polynomial equation. It's just 1, 1, 1, 1, 1. And we'll show you the graphical intuition behind like the multilinear polynomial. So the multilinear polynomial is technically like, you don't need to understand this yet, but multilinear polynomial is something like combination of straight lines. Like it's made up of linear. So like an entire polynomial can be like this, right? Like this could be a polynomial. Normally you see. Thank you. So like this could represent like a polynomial, for example, right? Or you could have like a proper cube, which could represent a polynomial. We'll show you how this is built, and based on this, you can develop some efficient algorithms. Like you play with this and you just like understand the nature of this, and then use this to kind of like do stuff. Normally, polynomials you see them as like this or this, like quadratic or whatever. Okay. So, does multilinear polynomials make sense? So these are some examples. You can see the 3x plus 4y plus 6z, right? All of them have power 1, and it's multivariate, right? Because of. Then you have this other one, xy. So what's the degree of this? Yeah, it's still 2, right? And the degree of this is 1. So technically the degree of the polynomial is 2. And likewise, this one is just 1, 1, 1. So the degree of the polynomial is 1. Make sense? Cool. So that's all. Those are the types of polynomials that we'll be interested in kind of.
For a multilinear polynomial, like you cannot have like just a normal number like that has like equals plus zeros. Like 3x plus 4y plus 5.
3x plus 4y. You can't 5.
You cannot find.
Yeah, you can't 5.
So it's just like
Maximum of 1. Yes. Exactly. That's more precise. So you can have a multilinear polynomial has a maximum variable power of 1. Does that make sense? Nice catch. Okay. So
Sorry, something you said, I think I kind of like loosely heard it.
yeah.
So you said polynomial, all polynomials are monomials.
All monomials are polynomials. Yes. Not the other way around. Yeah. Why are you asking questions? Bruh. No, serious. Yeah, I'm joking.
It's more like, I wanted to know, for the example, I'll say,
The degree?
say we have a polynomial 2abc
Uh-huh.
plus 3b.
Yeah. What's the degree of that? They should know that. What's the degree?
Why is it
ABC.
It's 3.
3? Maybe so that you don't want to be bigger than 3.
So you count. Yeah, so there are 2 monomials there, right? Let me write it down. Can you call the polynomial again? 2abc plus 3b, right?
Yeah.
Yeah. So you count the degree of each monomial. There are 2 monomials here. And the way you compute the degree of a monomial is to add up all the powers. So in this case, power is 1, power is 1, power is 1, right? So this entire thing has degree 3. This one has degree 1. And then the polynomial inherits the highest degree from this monomial. So that's why the entire polynomial degree is. Does it make sense? Yeah. Make sense?
Yeah.
Cool?
This is a linear polynomial.
Multilinear. Yeah.
Those ones are linear.
Linear is like a straight line.
Straight line.
Yes. So when you have
So
a
this
single variable, yeah, univariate but linear.
Yeah.
So something like 2a plus b, for example. No.
was a constant.
Yeah, so the constant.
But 2a plus 3b plus 4c is also univariate. Is that linear?
It's not univariate.
It's not univariate. It's multivariate. Linear.
Okay, it's all integrated.
Make sense?
How's that?
Yeah.
Linear.
No. Multilinear. Yeah, it's technically linear, but multiple variables.
It's 2a plus 5. Counts as a polynomial.
Yes. A univariate polynomial. No, it's made up of 2 monomials. So this is like a raised to the power of 0, which will condense down to Make sense?
Is it monomial like a linear polynomial?
A monomial, is it a what?
Is it a linear polynomial?
Only if it doesn't have a power in the variable. Do you get? So like this is a monomial, right? This is a linear monomial. So if you plot it, you have some straight line in some direction. But then if you have something like this, it's no longer linear. Actually, we could do this, to be honest. What's the name of that thing that they use? No, the other one, decimal system. So we'll just plot it out. So 2a, does it know a? 2x. So you can see it now, right? Like the straight line. And any linear polynomial, linear now, so one variable but no exponent, will always be a straight line, regardless of how many terms, because it's always collapse, right? Like if you have 2a plus 3b plus 6b, at the end of 2a plus 3a plus 6a, it will collapse down to 2 plus 3 plus 6, right? That's what 9, 10, 11. So if you do something like 2x plus 3x plus 6x, you can see that it's still a straight line. And this straight line, so I've hidden the other one now. And this straight line is equivalent to 2 plus 3 is what? 5 plus 6, 11x. So you can see that they're on top of each other, red and black. I can turn it on and turn it off, right? So it just collapses. So as long as there's no exponent, it will always collapse. And I don't know if you guys know anything about artificial intelligence, but like neural networks, there's something called an activation function. So the
Activation function.
yes, you don't need to understand this, so I'm just giving an example. There's something called an activation function. So the activation function is basically the non-linear part. Like it's necessary for that part to be non-linear. Because of if you have neurons like this and there's no non-linear part, then the entire neural network will condense down to a straight line. And you cannot really learn a lot with just a straight line. So you need like curves to fit or match things. You need complex structures. So that's where non-linearity comes in. The activation function. Who asked that? Activation function.
No, like we are talking about the neural network. I'm sure in the brain or something like that.
Yes, sir?
The neural network. Like in the brain, or you are just talking about
Artificial neural network. Even in the brain, so. Even in the brain. So there's something called an activation function that introduces non-linearity into
Is it
it.
like tablet?
Is it like?
Tablet.
Like, is it for like linear regression or something?
So, no, it's not. I'm coming.
Deep learning.
You know deep learning now?
Yes.
So there's value, for example. So see this value. This is not a linear function, right? You can see that it's not a complete straight line. It has like this and then this, right? Then there's also something like sigmoid activation. By the way, everything is related, kind of. Like AI, ZK, FHA.
That's for non-linear.
So it's also a non-linear function, yeah. So if somehow this was replaced with a straight line, then you cannot really do much with your neural network because of it will all collapse down to just one line, and you're collapsing down to linear regression basically. But it's just like an example of an advantage of non-linearity, just because of we're talking about that. It's not necessary for what we are doing so far. Okay, cool. Is there any other question? Ask as many questions until you get the intuition. 2AB. Ooh. So 2AB now, you can't just plot it on a... So let me show you something about the... So you know when we're plotting univariates, it's something like f of a, right? F of a is equal to some outputs. So let me use f of x because that's what these guys are using. So f of x is equal to some output y. So this means that you need two axes, right? So you need your y-axis and you need your x-axis. So whenever you put a value of x in here, there's a corresponding value of y. So this means that it is possible to plot it on a flat surface. But when you're now saying that 2ab, so it's now f of a comma b, it's supposed to be equal to some new value, right? Let's call it c. So this means that you need a 3D structure, right? Which is interesting. So you now have this, you have this, and you have something like this, right? So this could be your C, this could be your A, this could be your B. So AB is now picking a point on this, how do I put it? So this is just like A and this is B. So when you say AB, you're not picking a pair of points. So you're picking a point somewhere on the plane, right? And that will be projected up to C, right? So every point here has a corresponding value here. So it's a 3D structure. So you can draw objects, you can draw humans, you can draw everything. Everything we see is using this idea. That's why there's height. If not, everything will just be flat on the floor. Exactly. But the floor is giving us like the coordinates. And then it's now, so my hand like this now, there's like a point here. This is on the C. But then if you project it down, there's an equivalent point on the floor. So I guess our own, that's longitude and latitude. That's like the flat domain. And then there's now like the height. So it's now picking like, okay, where to be. But you can still do it. So I'll still plot it, but it doesn't get to. So there's something called Desmos 3D that allows you to do this. But I think they'll use effort. So you can see it now, right? You see the flat surface, right? X, Y, and then you see Z at the top. So so you see 0, 0. I'm not plotting anything. I'm just showing you how the point coordinate works. So 0, 0 is at the middle there, right? I don't know if everybody can see it.
Yeah.
Okay. So then you can have 1, 1, which is somewhere else, right? So this is like your input. Then if you have a function like that, 2a what? Plus, no, just 2ab. Yeah. So if you put 1, 1 in there, that will be 2, right? So that will pick 2 somewhere here. So that was just plotted at 2ab. They will call their own xy. So that will be 2xy. So this is what 2xy looks like, right? This is what it looks like. And it's huh?
The blue part of the line.
Yeah, the blue part. I think there's a way to zoom out.
You can't.
But yeah, this is basically what it looks like. So the blue is basically the corresponding C values for every single point on that plane. So if you do for 1, 1 and you project it upward, before you touch a blue surface, you touch it at exactly 2, right? Because that's 2 times 1 times 1, right? So you pick 2 and then you plot it upwards. Does it make sense?
So, why is it going below the green?
Why is it going down? Let's think about it.
Negative. Let's see now why it's negative.
So if it's negative, then I'm coming. Yes, so that's correct reason, but there's a more. So yes, x and y can be any value, right? So there's a corresponding C for any input. So that's why you have something that is going like that. I was thinking even function and odd functions, but I don't think that's relevant here. Does it make sense? So you can play with this. Just play with different like polynomials.
You do 2WXYZ. To scatter the shape.
So you can't plot it here.
You have another.
You need a 4D structure. Do you get? I'm coming. You need a 4D structure. So now you're going into.
That's why it's not fine.
Exactly. I like relativity. Yeah, you know after
Alright, so do we say this 2xy is a multilinear?
Yes.
But what I'm seeing is not
Yes.
linear.
What do you mean
seeing
it's not?
The shape I'm seeing is not linear.
Yes. It's not linear. I don't know how to put it. It's more like. So when we start talking about multilinear polynomials, we'll show you where the constraints actually hold. And also, I'm still trying to develop an intuition for why this works. So this is where like the math students will come in. So if you plot it on, there's a cube. We call it the Boolean hypercube, right? So the Boolean hypercube is where you put your multilinear point on. So the Boolean hypercube, how do I put it? The cube itself is a cube. You'll see that a cube. But then when you now expand it out, you now start seeing bends. I still don't know why. I'm thinking it's like maybe like a cloth, right? And then you can put some objects on the cloth at the middle, and it still looks like linear in that sense. But then once you expand it out, the cloth is still hooked to something. I don't know how best to explain it. So it just like warps it a bit, but I don't know the graphical intuition. If someone can figure that out, I'll be really interested in why that's the case. So when we get to multilinear, we'll now go deep into all these things. Make sense? Cool? Okay. So now we'll look at univariate in more detail. So we're no longer using this anymore, we're just going straight to the thanks. Okay, let's go. So my goal to do a lot today actually. My goal to finish Shamir at this pace because everybody seems to be getting it. Okay. So now I want to look at univariate polynomials. And we care now about evaluation and interpolation. Right? Those are the two things that we care about. So with those two things we can now do Shamir secret sharing, which is like the application. Then after that we'll forget about univariate and go to multilinear, and we'll spend some time there before we go back to univariate. Yeah. Yeah, no, it's not. But it's the same guy. Yeah, there are two. So Fiat and Shemer, but then Shemer secret sharing. So the Shemer is the same guy.
Shama was the one that co-founded RSA.
Also RSA, yes. So some people are cracked. I wish we had more Nigerians/Africans that were also cracked. We'll get there. Alright. So for univariate, we care about two things now. We care about evaluation. And we care about interpolation. So you guys should now start viewing it from, don't just look at it theoretically, do that, but also start turning the gears about like implementations. You get? So start trying to think about, okay, how might I implement this in code? Then if you have any questions regarding that, please ask. Okay? Alright. So we have interpolation. Then I'll teach you a technique for interpolation, and I'll tell you that there's a faster one. The technique I'm going to teach you is not what is actually used in production, right? Like production systems right now. It works, and it's the same. So like there are multiple ways to make rice, right? But one of them could be faster. But at the end of the day, you still have rice, right? So you can use this to do what you want to do, but there's a faster way to do it. We'll teach you the faster way to do it later, but I want you guys to try and do that yourself first, right? So if anybody can do that, just let me know. But we'll tell you how to do that later on. So if you want to play the game on level 1, you can just decide that, okay, you don't care, and then just wait until we teach you everything. But if you want to, because this thing is more like, the field is wide, like it's too wide. We cannot teach you everything right now. It's not even possible. What would be more valuable to teach you would be teaching you how you can go and learn this thing yourself, right? So we'll teach you what we can teach you, but then the skill I'm hoping you take out of this is like the ability to teach yourself, kind of, right? So you can now go back and now look at the field as a whole and say, okay, I like this part, or I want to explore this part more. And you can do that yourself, right? That's like the more important skill set here. So evaluation. So you always have a polynomial. Let's say you have f of x equal to 2x. Evaluation is basically you give a value of x and you say what is the equivalent output, right? So if you do f of 2, that's going to be 2 times 2, which is 4. Is this unclear to anybody? It's unclear? Okay. So this is all now. Then you already know. Okay, let's do something more complex, just in case. it's always x. We're doing univariate right now, so it's always x. So let's say we have 2x squared plus 3x plus 4. So what will be the evaluation at 3?
31.
I don't know what it is. I'll have to try it. Alright, let's do it now. So that will be 2 times what? 3 squared plus 3 times 3 plus 4. That's 2 times 9 plus 9, right? That's 18.
Can you reiterate?
You said?
Can you reiterate? Like, I don't get.
You don't get the evaluation?
Yeah.
Okay. So, did you get the other one? This one?
Which one? Yes, 2x. Yeah.
You got that one?
Yeah, another one.
So the algorithm is just that you are replacing x with whatever value you want to evaluate at, right?
Okay, you are the one giving it the value.
Yes, so you say, okay, I want to evaluate this polynomial, which in this case is f of x is equal to 2x squared plus 3x plus 4. And you're saying, I want to evaluate this at 3. So what you're saying, in essence, is that I want to replace x with 3, right? And then I want to simplify to a single output, or to the simplest form, right? So, in this case, we're replacing x with 3. So everywhere we see x in the original equation, we replace it with 3, right? So that x squared turns to 3 squared. And the x turns to 3, and then the 4 doesn't have anything there. Then you just simplify, right? So 3 squared is 9, then 3 times 3 is 9, and plus 4, then... Does it make sense? Okay, cool. So this one is for you now. No other person should talk. This is just for you. Say good already. Well, x was... There's no reason why I should not just teach. It's not different now. Just multivariate and multilinear evaluation. It's exactly the same idea. We'll see, sure. We'll see. Okay, Mitch. Evaluate this at 4.
Okay, so 4. Can I see the previous one?
No, you cannot.
So 4 times 4
Yeah.
plus 8 times 4 squared.
Yes.
So 4 times 4.
Let me write it for you.
Yeah. Okay. Okay, 4 times 4, so 8. 8. Sorry, 16. Sorry. Then 8 plus 16.
8 times.
8 times 16.
Yes.
Okay, so 8 times 16.
You don't need to do it, but
128.
why do you know that? Okay.
But, 16.
Is this 120?
Yeah. Yes, 16 plus 128. Okay, 144.
But you get the gist. Yeah. So the precision you can do that later. All right. Any questions? So I want to say that it's exactly the same thing for multilinear, multivariate, all those things, right? You are just replacing the variable with the value that was given, right? So if you have like f of a comma b, this is technically not univariate, but it doesn't matter. These are the simple parts, so let's just get over it as soon as possible. Nice. Right, so this is a 3-variable system. So I can replace, so you could do the full evaluation, which is like, let's say I'm doing 2 times 2, 3, 4, alright? So wherever I see A, I replace it with 2, wherever I see B, I replace it with 3. So this is 2, 2, 3, 3, 3, 4, right? This is 12, right? Why are you jumping step? 9 times this step 6, right? This was 6. Make sense? Okay, cool. Then you can do partial evaluation. It's something called partial evaluation. Partial evaluation is not possible in univariate. So partial evaluation is when you partially fill some of the variables, but not all of them. Makes sense? So in this case now, you could have done this partially. Right? Instead of f of 2, 3, 4 at once, you could have done f of 2 first. Right? So f of a, comma b, comma c, you can evaluate a at 2 alone. Right? This will give you a new polynomial that is just f of b, c. because A has been replaced. Does it make sense? So in this case now it's 2, right? There's no other A. So this is what. So this is our f of b comma c, right? See?
I was like, at A equals to 2.
As a equals to 2.
This is our f of b of c.
Yeah,
At
after-
A equals to 2.
Yeah, after
If it was
after
something else, our f of
b comma c will be something else, yes. So after partially evaluating the original polynomial at a equals to, you got this. But technically you can just call it like fbc, right? Then you now evaluate, let's say evaluate b at 3, right? So this is like 4 times 3 plus 3 times 3 c, right? So this will, we're going to get f of c here. This is going to be 12 plus, right? And then you can now evaluate this one at c, which is 4. So that's 12 plus 9 times, which is 12 plus 36, which is equal to what we had there. Make sense? So that's evaluation. Evaluation is simple. It's straightforward. So the next thing is, does anybody have any questions so far? Good? So next thing is interpolation. And specifically Lagrange interpolation. But there's a different way to do it, which is like FFTs. Yeah.
Sorry, this might not be important, but is there a reason to partially evaluate?
Yes. So some protocols that we're going to be talking about. Yeah, like some check. Oh, you guys, they gave an intro to some check already now. So like some check protocol now uses partial evaluation. Let me see if there's a more philosophical reason. So in ZK there's this idea of like interaction where you have a prover and a verifier. So you want to do things step by step, right? But then the verifier sends randomness. We'll get into the reason why all these things are done this way, but in order for the prover not to be able to predict what the verifier is going to do. So like if the prover is like the prover says that has a claim, okay, this statement is true. That's the prover's claim. And he wants to convince a verifier that the statement is actually true. So what happens usually is that the verifier says, I'm going to give you a test or an exam. And only if the statement is true will you pass this exam. But if the statement is not true, you're not going to pass this exam. But then, if the verifier doesn't use randomness, it's almost like the prover saw the entire test questions beforehand, right? And then the prover just wrote down the answers already and then just gave it to the verifier. So even if the statement is not true, the prover can do whatever it needs to do to make that test pass. So the need for the randomness is that the prover should come to the exam not knowing what questions will be asked of it while it's there in front of the verifier. Because it takes some work for the prover to try and cheat when they finally know the questions. So that's where the randomness now comes in. Then something like some check now takes those randomness through the partial evaluation, right? I'm sure there'll be a more fundamental, more philosophical reason why partial evaluation is needed in our context, but I have no idea right now. But that's good enough for now, at least. Okay. Any other question? We have time, so yeah. Which one? This?
Yeah, the other one. What should I call it?
Which one?
The one by the left. Yeah, that's one.
F.
Is it F?
Yeah.
Okay. So F, A, B, C.
Yeah.
So we can evaluate it. We can give any evaluation we want to. So let's say we give it 6.
Yes. For which
What
one?
would be like?
So you have to give an evaluation for each variable.
For each variable.
Yes.
So 6, 3, 2.
Yes.
We solve it differently.
Yes. It's not solve it differently, but you just replace. Anyway, you see A, you replace it with 6.
Okay. Can
Any-
you like do
For what? 6 what?
So, okay, A will be 6, B 3, then C 4.
Like this, right?
Yes.
Okay.
I just evaluate it.
Alright, no worries. So this is what? 2AB
Yeah.
plus 3BC, right?
Yeah.
So everywhere we see A, we replace it with 6.
Okay.
Cool. So that's 2.
So where is the 2 AB, where is it coming from? The 2 AB and 3, where is it coming from?
It's just a polynomial.
The one
An
that-
arbitrary polynomial, yes.
the one that put it
Yes.
in.
So it could be
So
any
it can be
polynomial.
4 AB will be okay.
Cool?
Yeah.
I should continue.
Yeah, continue.
Okay. So we replace A with 6, right?
Yeah.
B is supposed to be what? Then this other B is also going to be 3.
Yes. Okay.
And then C is going to be 4.
4.
Yeah. Then you just simplify.
Yeah.
So 2 times 6 is 12. 12 times 3 is 36. Then 3 times 3 is 12. 12 times 4 is 48. Then 36 plus 48 is 76 plus.
3 times 3 is 9.
Scroll it up so
Thank you. What do you mean?
like scroll
You can't
yeah,
see.
that's
Oh yeah,
it.
the back. 3 times 3 is 9. 9 times 4 is what, 36, right? So is it the same? Really?
Is the same? Yes.
Makes sense?
So that's the end of everything.
That's the evaluation. Yeah, that's the end of everything.
I guess it.
So it's the same thing for multivariate, multilinear, univariate. Very cool. Now the more interesting bits, this interpolation. So you guys need to be awake. You need to be awake a bit. Alright. Interpolation is the reverse. It's the reverse of evaluation. Yes.
So we solve it.
So you're happy to have a number.
It's not fully that, but it's like you have a set of evaluations, but you don't know which polynomial led to those evaluations, and then you're trying to figure out what that polynomial is. So you're trying to go backwards, kind of. We'll give an example, but I think I should state this fact. So a polynomial of degree d, so let's say so a polynomial that has a degree d, so d can stand for any degree now, right? Can be described with d plus 1 points. Does that make sense? It should not make full sense yet, well, soon. So a polynomial of degree d can be described with d plus 1 point. So this now suggests that there are 2 ways to write polynomials. You can write it the normal coefficient way, which is just say the 2x, right? Or you can write it evaluation way, which is now like the evaluations of that polynomial. So let's just give an example. So f of x is equal to 2x. What's the degree of this polynomial?
1.
So this means that it can be uniquely described with 2 points, right? D plus 1, which is 1 plus 1. So a point is now like an evaluation that's like x, y pair, right? So if I evaluate this at 1, for example, f of 1 is what? So a point here is, then I can also evaluate that, which is what? 4, right? So what I'm telling you now is that 2x is exactly the same thing as, let's say, an array of 1, 2, right?
So sort of like encoding the relationship between the points.
Yeah. And you can have multiple, because you could have used, rather than evaluating at 1 and 2, I could have evaluated it at 8 and 10. But the important thing is that I have 2 points that are from this particular polynomial. So once I have those 2 points, then I can always retrieve this 2x. And process of retrieving the 2x is interpolation. So interpolation is now, oh, you give me this, and then I walk my way back, and I get out 2x.
So at the end of the day, a polynomial with the power of, say, 7.
Degree, right?
With a degree of
7. We need,
you have 8 points.
yes, you need at least 8 points to uniquely describe it. So you could have like 10, 20, 30 points, but it must be more than that d plus 1. You get?
Must be more, or at least that.
Yeah, at least and more. No, greater than or equal to. Yes, correct.
So, why this we can interpolate back, right, from these 2 points?
Yes.
I think you can still use more than these 2 points, right? Like maybe 8 and 16. So,
What do you mean 8 and
It's
16?
not bounded, right?
You're saying that more than 2 points?
yes.
Yes.
Okay, so you can evaluate more than.
You can interpolate with more than, as long as it's more than, greater than or equal to that d plus 1. So I can get back this 2x from 1 to 2, 4.
Yeah. 4, 8, 16.
Yes, 4, 8, 8, 16.
Is the tuple the point or the number of elements in the array?
The tuple is the point. So there are 4 points
the
now.
point you are talking about?
There are 4 points now, right?
So that means the number of elements in the array is the point.
No.
That is this 4, 1, 2, 3, 4.
So this here is a point. This is like P1.
Oh, I was feeling the contents before was the point.
Makes sense?
Can you go back a little bit of?
So, it's safe to say that from this definition, we can say if greater or equal to
D plus 1. Yes.
Okay, because I didn't see it there, so
Yeah, it can be described with, okay, yeah, you could say greater than or equal to d plus 1 points. Or d plus 1 point. But it needs at least d plus 1 point to be able to uniquely describe it. Does it make sense?
But as someone just made 1 point, it was like, oh, 1 point. So it was like, if we have 2 points for any degree, or for any degree of polynomial, can't we just plot a graph and then get whatever we want for?
What do you mean?
Get any point on it from it.
If you have what?
If you have 2 points
From what polynomial?
for any power of polynomials, can't we use that to, it's not possible to use that to plot a graph also.
So only if the, how do I put it? Let's say if the polynomial is a degree 7 polynomial, those 2 points will not be enough to describe that graph, that particular polynomial graph. You need d plus 1 to be able to describe it. Do you get? So when we go into Sherman's equation, we'll now show you why, like a single point, multiple straight lines can pass through it, so it doesn't contain enough information to describe it, and on like that.
Okay. So I just like the Lagrange and this is the point.
Yeah.
That one's not too far.
Yeah.
And I go to it.
Yeah. So we'll go through this now, but I want to know if there are any other questions.
So, when you say describe a polynomial,
Yeah. I mean,
you're basically saying like interpolating the polynomial.
can get to the,
Yeah, like getting the polynomial back,
yes.
given the degree of the polynomial.
It will get back the same polynomial that the points came from.
Okay.
So like you have a polynomial already.
Yeah.
So the way I see it from an information theoretic point of view. So you have the polynomial already. The polynomial has information, right? So when I say describe, I mean that there's something else that has exactly the same amount of information that this has.
Yeah.
Which means that, and technically you know that's correct, because if you can take this and go back to that, then you already have the same amount of information.
So in that case, because let's say you're giving this point.
Yes.
So in that case, you're referring to this point as a polynomial.
Technically.
You can get a polynomial from it.
Exactly. So there's just two representations of polynomials. So you can represent the coefficient form, which is the 2x, where you have a coefficient and variables, And you can also represent it evaluation form, where you have just like an array of values.
So this is the evaluation point.
Yeah, these are the evaluation form, and this is the coefficient form.
Is it the same thing as polynomial over a field?
So no, now fields is just like another alternative for numbers.
Okay.
Like it's not relevant here per se. Right? Like when we're doing f of x and we said x is equal to 2.
Yeah.
2 could have come from the set of real numbers or from set of integers. It could have come from any set, including a field. You get? So in your case now, just abstract away that and just think of like, I can evaluate my polynomial at something. That thing could be a field element or it could just be a regular number. But the idea is exactly the same regardless of the set.
So the starting point now of that, of 2x that you did, that equals to that of, where was it coming from?
What? Where is what's coming from?
The 2x, that arrow that equals that of, where is
Yeah.
it coming from?
Where is what coming from? Is it the 2x or is it the arrow?
If that's, though that whole equation that
So 2x is a polynomial, right?
no, not there.
Well, I know. But 2x is a polynomial, right? And we're trying to figure out another way to write 2x. So we give a fact here, right? And the fact here is that a polynomial of degree d can also be described with at least d plus 1 point from that polynomial. So this polynomial, this 2x has degree 1, right? Remember how to calculate degrees. So that means that if we have 2 points from this polynomial, then we have fully described that polynomial. So I just got 2 points from that polynomial by evaluating it at 1 and evaluating it at 2, right?
Okay.
I don't even get what I mean.
That's cool.
So let me plot this for you. So look at 2x here. Can you see? So I'm going to now show that 1, 2 exists on it. Can you see this? That's the point. Then 2, 4 also exists on it. So then I can get 2 points that exist on that line. That's enough. I can forget about the line and just look at those 2 points. The reason being that I can now like just draw those 2 points on the graph, and then I can draw a straight line with my ruler through that, and that would be exactly the 2x polynomial. There's only one straight line that can pass through these 2 points. Does it make sense over? So it's restricting it. Yeah.
So, just to reiterate,
Mm-hmm.
this calculation is only possible for a multilinear polynomial. Like if it has anything larger than, for example, if it's 2x, it has a larger degree like 2x squared.
Yeah.
Can we still?
Yeah, but you use 3 points, at least 3 points now. Alright, so that's more like a quadratic curve, kind of. So that's c2x squared. So this 2x squared. No. Alright. So we have a point here. But we could have another point. So let's say, I don't know, this 0, 0. I think 0, 0 is a point. So you can say this too, right? So it exists on the line. But then this is not enough to describe a quadratic curve, right? It's only contain enough information. Like there are an infinite number of quadratic curves that can pass through this. And I'll show one. So there's a way to just interpolate like without stressing, but you're going to be implementing it, so you guys need to know it. What was the second one? 1, 2. So then I can just put like an arbitrary one here. So I'm creating like another quadratic curve. Oh no. Oh no. I'm trying to find one that is neat. No. It's linear, yeah. Huh? Which curve? I want a quadratic curve that passes through those 2 points also. I don't know how easy it will be to use. Let me just try it first and see if I can easily just paste this in here. Yes, okay. So you can see. So this is why those 2 points were not enough to describe it. So now we have two different quadratic curves that are passing through those 2 points. So it didn't contain enough information to uniquely fingerprint this particular one. So that's why you need a third one. So that's where that d plus 1 comes from. So a quadratic curve is of degree 2, because the highest power is x squared. So you need 3 points, 2 plus 1. So once you have 3 points now, there's going to be only one quadratic curve that can pass through all 3.
I have 4 points.
You can have 4 points. So if you have 4 points on it, there's still only one degree 2 curve that can pass through all 4. Yeah, but then there's not going to be a degree 3 curve that can pass through. Yes. But in our case now, we're looking for a degree 2, so that's why we just need that. Does that make sense?
So,
Okay.
Is this synonymous to, okay, no, there was a different way, there was a different way we normally used to get these combinations. So, from what you explained now, when you say to get the, what's it called, the points, number of points that is needed to describe a polynomial, you make use of the power,
The degree.
the degree of the polynomial plus 1.
Yes.
So before now, we're using 2 raised power of the number of variables, and
Are you talking about yesterday, some check?
yeah, when we're going through subject.
Okay.
So if, like the polynomial I used, for example, that I said the degree plus 1.
Yeah.
So where is, and the degree is 1 plus 1 and gives you 2.
So that's 2x, right?
Yeah, that's 2x. So and for that same 2x, if you want to use the other way, where you say 2 raised power of the number of variables, you do 2 raised power of 1 is still 2, and that works too.
Are you saying that, are you trying to figure out an alternative way to figure out how many points you need? Or what are you trying to figure out now? So the
So
1 plus 1, right? The first, this one I just described,
yeah,
d plus 1,
yeah,
tells you the number of points you need to pick from that curve, right? To be able to reconstruct it later.
that's the number of possible combinations.
It's not necessarily the number of possible combinations. It's not. So what you're talking about now is you're thinking about the Boolean space where you have 0, 1, 0, 1, 0, 1. So that 2 raised by this is like the power set, kind of. Is the number of, but that's not related to this.
Okay.
Yeah. The number of subsets. That's not related to this right now. Because you can just break it. Just find let's say like a degree 2 polynomial, right? That will need 3 points, right? To call 2 plus 1. Then try and use that.
Oh, yeah.
Yeah, so that just breaks it. So you can just, it's not the same. Yeah.
Like, how many points are on this board?
Yeah, an infinite number of points. Huh? Oh. Yeah. Depends, right? It depends on the sets, right? It depends on the set, the domain you're evaluating. So if you're evaluating over the real numbers, then they're infinite. But then if you're evaluating over like a smaller set, so let's say like a finite field, then it's no longer infinite. It's just like based on the set. So if you're evaluating over a finite field of like mod 7, so that just has 7 elements. So it's only going to have like 7 values. But it won't look like this anymore. It'll just be like dots on a space.
Or it can be a falling 8.
It could be a what?
8 that fell down.
What?
When you're talking about that would be like 3 points.
Yeah.
And you just said if you have 3 and also pass through.
What's it?
Like you need 3 points to uniquely address
A quadratic.
So I say you can have 4.
Yes.
But then now you say we have 3. 3 can also pass through those.
We have a degree 3
Yeah,
polynomial.
can also pass through those.
Yeah.
So what's the definition of 3 now degree 4 for these 2?
What's the what? No, just something. I'll understand. I'll ask questions that.
So this degree, see, these 2 degree now we need 3 points.
For a degree 2 polynomial, you need at least 3 points.
3 points.
Yes.
So at least, so if you now have 4 now.
If you have 4 points from that degree 2 polynomial,
But 3 degree can also pass through that 4.
A degree 3
So what's the
polynomial.
definition of us not using 4 instead of using 3 for these 2?
What's the what?
The implication of using 4
So,
for these 2 instead
when you are doing the interpolation, you kind of like need to know. No, you don't need to know. Wait, let me see. I'm coming. Lagrange will collapse now, right?
As much as those points are on its own,
Yeah,
it will collapse down to
the minimum. Yeah, it's collapsed down to the minimum degree that can pass through it. But technically, there should be a degree. So, like, let's say you had 4 points, there should be a degree 3 polynomial that can pass through those points.
through 4 points.
Yeah.
That's only the fourth point is on the polynomial. It's just like 2 points can represent a straight line.
Yeah.
But on that straight line, you can pick 50 points. And if you interpolate those 50 points, are still going to get
The straight line.
the straight line.
That's if we use Lagrange, right? But technically, those 50 points could be passed through by a higher degree polynomial, right? Like, you could imagine that. Yeah, you can just like do zigzag. Yeah. Yeah. It could technically. It is last long.
Is it safe to say that when we are getting like a degree 2 polynomial, we should only use 3 points?
Not only, no. Lagrange interpolation will always collapse down to the smallest that can pass straight, right? So if you
use 4 points to still collapse.
yeah, it still collapse down to just a straight line, right?
So, based on that assumption for the last statement,
Okay.
like if we have 50 points, which is a linear, that 50 points on a linear
On a line.
also,
That
a higher degree polynomial can actually pass through the 50. Because I was thinking higher degree polynomial will create a curve, and a curve, no matter how we try to make it, will not go straight.
And it will be straight.
Bend at point, so if you try to curve out.
Yeah, it will curve out, but it will touch all 50 points. The point is that all 50 points are on the line itself, right? I will draw it out, don't worry. Can you see this? So you could technically have this, right? And then you have like a straight line that passes through. But also you could have this and have something that goes like this.
Oh.
But it still passes through everything. But now it's a higher degree polynomial. So that's what I was saying. The 50 points, one straight line could pass through everything, but technically a higher degree polynomial could also pass through everything. I just don't know how you can now get like, let's say I'm saying, okay, I want a degree something polynomial. I know that Lagrange interpolation collapses down to the smallest. But I wonder if there's a way to pick.
Okay, where you want the points.
Yeah. I don't know if. Yeah.
The points will define.
Oh, I know how to do it. Yes. You can put random points. Do you get what I mean?
But if those random points
I also collinear and it won't work, right?
if they are not if one of those points is not like linearly dependent on another,
Yeah.
it will not
Yeah. But you can do a randomized algorithm where you're just shuffling the. Yeah. So what I'm saying now is that. Is this this is not necessary though. It was just we're just riffing. but what we're thinking now is let's say I wanted to get a degree 2 polynomial. It's not even possible now. A quadratic polynomial can never pass through this. Quadratic polynomial can never pass through. Can it? It can't now.
No, I think we can try it.
No, it-
This, for instance.
Let's use Desmos.
No, it's not even a Desmos. I'm coming.
Now, what I was even thinking was that a quadratic polynomial kind of passing through.
It can't pass through this. No, quadratic cannot pass through this. I think
That's
there's
what I was saying, like that if you eventually try to curve itself out of.
yeah, but a higher degree polynomial can pass through all this. What I'm now thinking is that there's a limit, right? That let's say quadratic now. I don't think a quadratic can pass through this, regardless of how much you bend it.
What do you call that? You're talking about QAP.
Like, like this.
Okay.
That's just one inflection point, and then the rest are just. Can it pass through this? I don't see how you can bend it. Yeah, the 3.
The quadratic is 3 degrees.
Oh, the hand, right? Yeah. So, what she's saying now is this, right? You go like this, something like this. So technically, it could pass through. It will pass
Pass
through.
to 50 points.
So these 3 points.
And 3 points.
All of 50. Yeah, but if the 50 if they are scattered, then it can't really pass through. But that makes sense. That makes sense. Can be anything. Can be anything. I was just specific about quadratic for this case.
So the curve can be any kind of curve.
Yeah, it can pass. Yeah, any higher degree curve can pass through.
And then when you
But right now, I'm just. This is not necessary. All these are not necessary. I'm just trying to see something. Yeah.
when you say quadratic,
If you are given like 4 points
Yeah.
to get like degree 3
Yeah.
for a point, you get
For the 4 points.
polynomial of that class, right?
Okay.
Given 4 points. But you said Lagrange will definitely collapse
So the smallest degree polynomial that can pass through all 4.
and they are going to get degree
So you are saying now that what if there's a smaller, let's say a degree 2, that can pass through a degree 1,
2.
but want to get degree 3 specifically?
Yeah.
That's what we were thinking about just now. So what I was thinking was that you just add more random points to it, right? So you have the 4 points, so like P1, P2, P3, P4. Then you first of all do your Lagrange interpolation, and you now realize that wait, I got a straight line, right? A degree 1. So that means that all those 4 points are on that straight line. So what you need to do now is I think you need to start injecting random points, right? And then randomize the algorithm. I don't know if there's a more precise way, but this is where I could just come up with now. So you inject P5, maybe P6, and then you test, you see, is it still on that straight line? So if you get a point that is not on the line, then it will have to bend, adding a degree. So if I get a couple points that are just that force a bend, then you can get like any degree that you actually want. You get? So the only thing now is that the 4 points impose a minimum, kind of. Like there's a minimum.
Using Lagrange, there's no way you can get from 4
That's what they
points.
randomized
It will
out.
now get, there's no way it will get to, like having 4 points. There's no way it will get to a degree 2.
It can't. If you got the 4 points from a degree 2 polynomial, it will. So like let's say the degree 2 polynomial is this, right? And then you got this point, this point, this point, and this point. If you use Lagrange, you'll get back the quadratic curve, which is a degree 2 polynomial. So it always picks the smallest degree curve that can pass through everything.
I was thinking of the power that it will not.
What power?
Like, I don't know, like when you are in the Lagrange equation.
Yeah, but the only power that you should care about here is the power of the polynomial that actually produced the points, right? And the power of that polynomial was 2, right? So the degree, I mean, was 2. So regardless of how many points you pick from it, Lagrange will always find the smallest one to go back. That makes sense? No, this is not supposed to make sense though. Let's go to this thing. Yeah.
I guess like how to explore this, but like the Friday degree test.
Yeah.
Because like an infinite number of polynomials can pass through those 4 points.
Yes.
These 4 points now, an infinite number of polynomials can pass through.
Yeah.
But there is, since it's 4 points, there's just like one degree 3 polynomial that can pass through.
Yes.
Like when we're specific about like degree 3, there's just one degree 3 polynomial that can pass through those 4 points.
Yeah.
But there are infinite number of polynomials that can pass through the 4 points.
So it's not be above. So
Yes.
degree 4, degree 5, degree 6.
Degree 5, degree 6.
So that's that d plus 1.
But my own question, if the two polynomials pass to that point,
Yeah.
using Lagrange, we still get back to
The degree.
Yeah.
So what if you are not specific? That's what you said, and just randomize.
Yeah, potentially. There might be a better way, but that's the one I can come up with.
So the only way, let's say we have a degree 2 polynomial, and then we have 4 points that fall on that degree 2 polynomial.
Mm-hmm.
That means those 4 points are actually on that polynomial. And with 3 points, then we need like 3 points to represent the degree 2 polynomial. And with 3 points, and if we throw away one of those points, we'll still be able to reconstruct. I don't know. Hope I'm not confused.
No, it makes sense. But then now there's randomization for the. So what Francis is saying now is that, let's say I had this 2x, right? You could technically, you could interpolate it with this. I think. Can you do this?
I am randomly lost.
Who's lost? So you see this, right? It's 2x is a degree 1 polynomial. And because it's a degree 1 polynomial, you only need 2 points down on it. So these are 2 points, and that's the 2x there. So any extra point is not really adding information. Like, let's say you put 2 and 4, and you put 4 and 8. It's not adding information. It's still going to give you 2x. So you're just like redundant information, kind of.
They're kind of like
for that,
linearly dependent. Those
Yes.
linear points can be-
Exactly. Yeah?
for this operation you are doing, the first one does always have to 0 zeros.
Depends on the function. Like 2x plus 5. Are you saying that
What
should.
if now is 2x back?
Yeah, 12.
Okay, 0, yeah.
2 times 0 to 0. But 2x plus 5 will be
But
5.
even if you don't put that 0, 0,
It doesn't matter, yeah. So I could remove this 0, 0 now and just use this 3, and I'll still get 2x. But I could also remove this one in the middle because we only need 2 technically. So all these other ones are just redundant. So as long as I have 2, I'll always get 2x.
what if it's just for 3 evaluation points? So you need like
If it's a quadratic curve, then you need 3 points. So if it's a degree 2 curve, you need 3 points. But any 3. So you can just pick randomly as long as it falls on it. Yeah?
So my question is it possible that something is a degree 3 polynomial, for instance,
Mm-hmm.
and then you are trying to interpolate it with four points,
That's what you should.
and then we are trying to interpolate it. Now we know that it's a degree 3 polynomial.
Yeah?
And then now trying to interpolate it from 4 points.
Mm-hmm.
Is it possible to actually first, using Lagrange, is it possible to actually first eat possibly maybe a degree 2 polynomial that passes through those points also? Or will Lagrange actually first eat that degree 3 polynomial that passes through those points?
It will hit the lowest. But in your case now, you already made the assumption that the polynomial was a degree 3 polynomial, right?
Yes.
So it will always hit the degree 3. There is no degree 2 that can pass through it. Do you get? It's the same way, like, if you pick 3 points. Wait. If you pick 3 points from a quadratic curve, right? Degree 2. There's no straight line that can pass through all 3. Regardless of how you it has to bend one way or the other. That's what I mean. So once the point has like a minimum polynomial degree to pass through, Lagrange will find that one, and you can't find anything under that, because nothing under that can pass through.
You can just add like a random point to this.
Are you serious? I was not even showing my screen. Sorry. I drew something. So this is what I was talking about. So you have 3 points from a quadratic curve.
Yes.
There's no way a straight line can pass through all of this.
Yes.
It's not possible. So Lagrange will find this one and not find a straight line.
No, we were talking before. He asked a question before just now that if probably maybe we are interpolating in 4 points, we are interpolating 4 points, and it bounces to a quadratic equation, whereas we are looking for a kind of cubic expression. You know, like, and you said you just add more, you just start adding random point and stuff. So that's why I was asking, like, is it possible that if it was actually like a cubic expression, is it possible that it will first eat that a 4 point input now, will first eat a quadratic expression instead of eating that cubic expression?
So for I don't it will eat the minimum. Okay.
Let's say you have like 2x,
Yeah.
right? And now minimum of 2 points.
Yeah. Yeah.
Right. But now you're now saying that what if like there's another polynomial, right? That is like 2x squared.
Yeah.
And that's like minimum of 3 points. And 2 of those points can also like is it possible for if 2 of those points are similar to 2 of the points that form 2x,
Yeah.
2x polynomial? Is it possible that
Yeah, but you can't interpolate the 2x square unless you have 3 points now, right? And those 3 points I don't think will collapse down to the 2x, yeah?
I think
Or you want to?
it's not possible.
Yeah.
The reason why is that in Lagrange interpolation, the polynomial is always unique, irrespective of the point given.
It's always unique
Irrespective of the point given.
for Lagrange, right?
For Lagrange.
Yeah.
So irrespective of the point given to you, maybe you are given 100 points or infinite number of points, it will still fall back to the minimum of that distance. So you need not to worry about whether there is higher degree or that distance. So
And in practice, we don't actually know what the degree is going to be.
So meaning that any point, any expression that those points falls back to.
That's it.
That's it.
Yes, that's it.
So like meaning that even if you have even if you add more, because you know like I'm asking this question because a question was asked where you say what if you are looking for a cubic this thing and it falls to quadratic and say you add more points. So meaning that even if you add more random points and stuff, it's still going to fall back to the
No. Unless you pick those points from the graph. Do you get? Why I was saying random points, just pick arbitrary random points that might not necessarily fall on that graph. Exactly, that will change it. So that's why you can now maybe get a higher degree polynomial if that's your intent, right? But that's usually not the intent in these systems. You just want to get the minimum that passes through that.
so most of the time you don't know the degree.
Yes.
So
Yeah, I know.
any degree you just
Okay. So let's go to the mechanics of interpolation now. Do you guys want to take a break?
No.
I just can't
We are not used to fire down.
Huh? Oh. Okay, to eat? Just to rest. No whatever. So interpolation now. Are you ready?
Yes, sir.
So for interpolation, we have a set of points already, right? And we're trying to figure out the polynomial that would give us those points, okay? So, let's use the one that we did. Where is it? Yeah, 2x. What was this thing?
1 and 2.
And 2 and 4. Right? So this 1 and 2 are the values of x that I want to put into the polynomial, right? So what we're saying is that we want to find a polynomial such that if you do f of 1, you're going to get 2. And if you do f of 2, you're going to get 4, right? So there's a way to construct this. There's a way to construct it from the interpolated set, and this is also the way you do for multilinear. So if you understand it now, you probably can't understand it. The general form is this: f of x is going to be equal to your interpolating set, in this case 1. No, sorry. The output you want to get. So 2 times something, right? L0 of x, right? Relax. Huh? I've not defined it yet. It's just a function. I'll tell you the behavior of the function, then I'll tell you how you can construct the function. It's just wait first. And just wait first. Okay? Just wait. Alright.
Wait small.
Yeah, just wait small. Right? So 2 times L 0 of x and 4 times L 1 of x. Okay? This is the general form, regardless of multilinear or multivariate or whatever. It's always like the output times something plus another output times something, right? And then what's the idea here? The idea now is like this thing has to behave in a very specific way. So remember I said when I do f of 1, I'm expecting the answer to be 2. What will make the answer 2? If this entire thing collapses down to 1, right? Then I need to also get rid of this 4. How do I get rid of the 4? If this collapses down to... Does that make sense? So I want a function that if I pass in 1, this L0 of x would evaluate to 1. And every other thing will evaluate to 0. Do you get? But then if I pass in, let's say 2, then is this other one that will evaluate to 1? Why this one will evaluate to 0? Yeah?
Kind of confused because what you said now, there are multiple ways that from this equation now you can actually arrive at that same thing. So you said when you put the first one you said, which was like when you needed 1 here and 0 here.
Yes.
Yeah, 1 here and 0. I think you're trying to look for, you're trying to get 2 as final output.
Yes,
So
f of 1 is
1, 0.
Yes.
Then I could have just said this would have been 0.
What could have been 0?
That one could have been half.
Yes, you could, technically. So this is where creativity now comes in, right? So the actual Lagrange is what I said. So these functions can only be 0 or 1, right? So it's restricted in that sense, right? It's only 0 and 1 for the interpolating set. So the interpolating set here is what? 1 and 2. So the functions are related to 1 and 2, such that as long as your x is from that interpolating set, they behave as binary values. So they are like selectors. So they select an output. But then there's no reason why. You need to now start seeing like the generality of the idea, right? You're trying to fit something. So technically, I'm sure you should be able to do it with a more complicated structure that maybe starts to include half. But then you need to make sure that it works for every point. So you need to now like define like a proper system. Yeah?
But if you use half, you're going to get 2L1 there. It's not going to be 2.
That one will be 0.
No, the other one will be 0.
Yeah, this will be 0. This will be 2L1, not 2.
No. So see, this will be like 2 times 0, right? Then plus 4 times 1 over 2. Do you get? So this will be 0 plus 2, which will be 2. But this is not how it's done, no? This is not how like we are going to do it. But I'm not saying that is not necessarily a stupid idea, right? Like, I'm sure you can build a system around that potentially. And that's like what the research side of things, you try and look at structures and you try and figure out ways to do new stuff, right? So in our case now, this L0 and L1, they're called the Lagrange basis. Yeah? I don't think so, to be honest. I thought I did. but I don't know if I did. It's not there. So it's just not working. But OBS is recording, so the hope is that OBS captures it. So L0 and L1 collapses down to binary once you take a value from the interpolating set. So the interpolating set is here, 1 and 2. So you put in a value. I'm trying to show you how maybe one could have reverse engineered Lagrange. Like you have the goal. The goal is to, if f of 1 is there, give me 2. And if f of 2 is there, give me 4. So it's like a selector. So you want 2 should be selected when 1 is passed in, and 4 should be selected when 2 is passed in. So that instantly tells you what the behavior of L0 and L1 should kind of be. So it should turn to 0 when L0 should turn to 0 when you want to get like 4, and L1 should turn to 0 when you want to get 2. Does that make sense? Okay. So the question now is like, what is the actual function? So like now, as I'm talking to you now, I don't know I've forgotten what the actual function is, but we'll figure out how to get it back. We'll reverse engineer it somehow. So I know that the idea is division, right? I know there's a division in there. So it's like, if you have a divided by a, you're going to get 1, right? And if you have 0 divided by anything, you're going to get 0. So this is the property that we're going to use to kind of like reconstruct everything. So the way it works is that you do x minus every other thing in interpolating set. So now we're doing for this L0 cares about what? It cares about 1, right? Like it's paired with this, right? So when it sees a 1, it wants to turn to a 1. You get? Why this other one is paired with what? 2. So when it sees a 2, it wants to turn to a 1. So we can map it.
So the 2 is not the y, it's not the y that's
it's the x. Yes.
Like, you know, there are 2 2's.
Yeah, I get what you mean, yes. So it's this one here. We'll do more examples, eh? So don't worry about not getting it immediately. Just get the general form, then we'll now do more examples. So this one is this, and this one is this. You get? So it's the x values. The Lagrange basis polynomials only care about the x values. Yes. Why these other ones are now the output. That's the only place to use the output. Does it make sense? So these two things are what we're going to kind of like use to derive the Lagrange basis algorithm. So one is a situation whereby when it is what you're expecting, you collapse to 1. But when it's not what you're expecting, you collapse to 0. So let's say something is expecting a 1 from this 1, 2 set. Let's use a bigger set, because I think it's more instructive there. So let's say we had these 3 points, 1, 2, 3. I wanted to create a polynomial that if it sees 1, it will collapse to 1. But if it saw 2 or it saw 3, it will collapse to 0. So for something to collapse to 0, this is one way. I'm sure there might be multiple ways for something to collapse to 0. But the top has to be 0, right? So in this case, we want something that when you see 2 and 3, the top becomes 0, right? So what we will do is that we'll say x minus 2 times x minus 3. We don't do x minus 1, right? So now if there's a 2, it will be 2 minus 2, right? Which will be 0. Then 0 times whatever is just 0. So 2 cancels itself out. If there's a 3, then 3 minus 3 will be 0. So everything collapses. Does that make sense? But what if it's a 1? If it's a 1, then this becomes 1 minus 2, 1 minus 3. So that's our A. So what do? We just copy that on the bottom, right? So we know what it will look like when it's a 1. It will be 1 minus 2, 1 minus 3. So what we need to do here is just write 1 minus 2. You get it now. So if it's 0, it would be 0 over this, which will be 0. If it's a 2, it will be 0 over this. If it's a 3, it will be 0 over this. But if it's a 1, it will be 1 minus 2, 1 minus 3. Divided by 1 minus 2, 1 minus 3, which will be 1. Does it make sense? You don't need to even multiply it.
So like what you are doing is just giving us like in any situation where we forget the formula, we can just come up with the formula and
Because
remember it at any point.
yeah, potentially like formulas, you don't need to memorize formulas here. And especially if you are going to do research, you need this like ability to kind of like, so whenever you're learning anything new in this sense, you should try and figure out like how can I have come up with this myself, right? Potentially, like try and reverse engineer it to like the barest form.
So what we're doing is we're deriving Lagrange.
Yes. Yeah, just based on like the goal. The goal is that f of 1 should be this, f of 2 should be this. So that now suggests that I could just put the thing that it's supposed to be, and I have a selector in there, and I have the behavior of the selector. It should be 0 when I see this and this. It should be 1 when I see this and this. And then we now saw that a over a can give you 1, but 0 over a will give you 0. So the things that we want to kill, we need to figure out a way to turn them to 0, which is what we did here. So x minus 2, x minus 3. Because if you put it there, it will subtract itself, and then to be 0, then everything will be 0. So that's where you get the second case. But then you now need to know, okay, how can I do the first case? So the thing you're looking for will be 1. That's why we didn't put 1, x minus 1 there. Because if we put x minus 1, it's have turned to 0, which is not what we want. So that's why we had to remove the x minus 1. So you can put x minus, so now imagine, okay, if we put 1 here, 1 here, you have something on top. It could be anything. But if you divide it by itself, then it will always be 1. So you just replace x with 1, 1, and put it at the bottom. So this is how you can pick out 1. So now let's test it out. Right? Let's try and evaluate this at 1. It's obvious though, bro. Let's just do it. The rate at 1, that's what? 1 minus 2, 1 minus 3, 1 minus 2, 1 minus 3. You guess. You could, but technically you could just like say 1 over 2 cancels 1 over 2. So it's still 1, right? But technically you could. Yeah.
We have 1, 1, 1. Like I'm just saying, if you add 1, 1, 1.
Okay, I'm talking about in general now. What's the goal?
Like 1, 1, in place of 1, 2, 3, we have like 1, 1, 1.
The same point.
Oh, the same point, doesn't
Yeah.
Shit,
So exactly the same
I was trying to
interpretation.
say that, I was going to say A over A equals 1 equals
Yeah,
0 over 0.
yeah, undefined, yeah. So let's now make another function that can pick out 2, right? It can pick out 2, but if it sees 1 and 3, to turn to 0, but if it sees 2, to turn to 1, right? So we need to remove what? 1 and 3. So we need to subtract them from themselves. So x minus 1. So now if 1 and 3 comes, the top will be 0. Everything will be 0. We don't care again. But then if 2 comes, what will happen? 2 minus 1, 2 minus 3. So just write it under. Is that easy? And then this is something that can pick out 2. But if you put in 1 or 3, it doesn't pick it out. Does this make sense? So what would the one that can pick out 3 look like?
No, 3 minus 1.
Better. It's not supposed to make complete sense, but how many people get it? Just raise your hand if you get it. Okay. You don't yet get it, right? So right now, forget about Lagrange, right?
So, is it like a compound function?
No, I don't think so.
Those coefficients.
What coefficient?
Like when you have one function, when you're trying to like
Improper function is something like what? 3 over 2, right? Which is like
no,
1.
like division of that we use how should I say? Like partial function. Partial function.
What's a partial fraction?
Now we use
Splitting,
I don't know what a partial fraction is.
like splitting the composite fraction into like simple,
Give me an example.
like let's say you have x squared minus 2x plus
Or 1 over x
Yeah,
plus
over
1.
x
X plus
So like a quadratic denominator.
Yeah.
And I'm splitting it into like
Two functions
yes, they are just
that you
like
multiply.
single-
The roots, basically.
yeah.
Yeah. That's a partial fraction.
Yeah.
Why is the fraction there?
And if you are splitting
The aim is that you don't know what they add together as a single fraction. But because that's a variable, they're not trying to tell you that I have this now. What did the person do to get this? So you now use partial fraction to split it
Okay.
to get what the person did.
let's say you have 3 over x plus 1 over x.
3 over x plus 1 over x.
Gives you like 4 over x. So partial fraction is like taking 4 over x
And then
splitting
splitting it back
yeah,
into.
the two.
Okay. Yeah, I get that now. So, what do you mean now? Can you reiterate now that I have more context?
Yeah, but when we try to solve it, like in the course of doing our partial fractions, we do all these denominators of the doing.
Okay.
So we try to get where we can get each similar fractions. So what I'm looking at is that I'm seeing that we are replacing the denominator by each of them, so that the one that is not zero.
Yeah.
So I was like, it's the same logic.
It's not. I don't know if it's the same logic, right? Because I don't know that logic. But mine is coming from a much simpler point of view, where it's like, if the numerator is same as the denominator, the answer is going to be 1, right? And if the numerator is 0, the answer is going to be 0. So using that relationship, we can construct these L functions that I was talking about, which has exactly the same behavior. That like when it sees a number from a set, it should be 1. But if it sees any other number, it should be 0. Does that make sense? So I don't know. So we can look at it later and see if there's a relationship there. But right now I don't know if there is. Makes sense? So I need to do it again, right?
Yeah.
Not Lagrange, oh.
Yes.
This is not Lagrange yet.
Yes.
We're talking about the L functions, right? The Lagrange basis functions. So let's do another set. So let's say we have this set now. 2, 3, and 5. Right?
2, 3, and 5 are points.
They are the interpolating sets. The x's.
The x's.
Yes.
Okay.
Yes. So we want to create a function that will evaluate to 1. So now this is really interesting, right? Because if wait, how many people are getting this?
We're getting it. We're getting it now.
I get to you, but it's a question.
Now you realize if we are getting it.
Why are we using just one?
Let's make
Why are we using simplify?
Yeah.
Anything extra.
Yeah. You know, you can take arbitrary points, right?
I don't like this thing.
So like f of right? F of x equals 2x. Then we got 2 points. Okay? So these 2 points, it could be arbitrary points. As long as it's 2 points from this. Right? It could be arbitrary. So it could have been 1, 2, 2, 4. It could have also been 4, 8, 92, 184. It doesn't matter. But these your L functions needs to respect the x values. They need to respect it. So now I'm showing you how to construct the L functions regardless of what the x values are. So the first one I showed was how to construct it when you let's say you have 1, 2, 3. Now I want to do with like 2, 3, 5, but it doesn't matter. The point is that you have a set. You want a function that once a particular element in that set shows up, it will say 1. But if any other element in that set shows up, it will say 0. You get? So it selects for a particular element in the set. And why we're doing this is because of, we said that when we get f of 1, we should get 2, right? And when we get f of 2, we should get 4. So we need something that once it sees 1, it will say 1. But then the other guys should not look for 1, right? So this first guy is looking for 1, while the other guy is looking for 2, right? So once this one sees 1, it's returned to a 1, right? Because that's what it's looking for. So then it will be 2 times 1. But this other guy is not looking for a 1, right? He's looking for a 2. So once it sees a 1, it's turned to a 0. So that will be 4 times 0, which will make it disappear, leaving 2, which is what we wanted. F of 1 should be equal to 2. It's not clear yet. Do you know what is not clear? Can you? Yes.
So now, the whole calculation, the whole all of this.
Yes.
But what I want to understand is why. Now.
Okay.
What I want to understand is why. So now you're saying that
We're trying to get back.
We're trying to get back 1, but now
2x.
Yes. So you're saying f of 1, right? Anytime you put anytime you get, let's say the polynomial is 2x or whatever the polynomial is, right? Whenever we put 1, we're going to get this value, right? So look as if you're duplicating something. You're trying to find 1. You're trying to get 1 when you put 1.
Yes. But you're talking about this L function now,
Exactly.
right? The one that is looking for 1.
Yes.
So when you put 1, you're supposed to get 1.
Yes.
Yeah. But technically, it could have been anything, right? That one, the 1 is just a coincidence. But you could have been, this one might have been looking for 3. If it finds 3, it should still split out 1. It's always going to split out either 1 or 0.
And then the other one will be 0.
Yes, and then all the other ones will be 0. So it's always trying to spit out 1 or 0. But it just happened that it's also looking for 1, which is why it's spitting out. But it disconnects the input and the output. The output is always 1 or 0. So you have a function that is looking for something. If it sees this thing, it will spit out 1. 1 is like, yes, I found it. 0 is like, no, I couldn't find it. You get? And it can be looking for anything. So it's still not clear. But do you now have a hint as to what?
I do have a hint.
You don't have a hint. Oh yeah, what is not clear?
Just consider if I get something now, ask a question.
All right. So now I want to do 2, 3, 5. I want to find a polynomial that looks for 2. Okay? If it sees 2, it should give you a 1. If it sees 3 or 5, it should give you 0. Yes. Something has clicked. Okay, good. Welcome to the other side. So 2, 3, 5. 2, 3, 5, right? Okay, cool. So what I'm going to do now, I'm going to even simplify it so that the relationship is not so obvious. Okay. So once you create something that, the way I prefer to do this, I made a mistake. The way I prefer to do this, I like to write the thing that the polynomial is looking for under, right? So what I'll actually call this normally is like L2. So that it's obvious that this polynomial is looking for 2. Do you get? So if 2 comes, it will give you a 1. But if anything other than 2 comes, it will give you a 0. Okay. So now we're looking for L2. So what are we trying to destroy? 3 and 5, right?
Yeah.
So we need them to become zeros.
Yeah.
At the top. So that will be x minus 3, x minus 5. But then, we didn't destroy something, we didn't destroy 2. So if, yeah, we're looking for. So, but we need to make sure that if 2 comes, the top and the bottom is exactly the same. So now we can look at what the top will be when 2 comes, which will be 2 minus 3 and 2 minus 5. So we just put that at the bottom also. Does that make sense? Now let's simplify so that it's not obvious. Because right now it's obvious that this works. But let's now simplify it down to something more granular. So what would the base be? 2 minus 3 is minus 1. 2 minus 5 is what? Minus 3 times minus 1 is?
3.
So the bottom is 3, right? Yeah. Then let's multiply this one out. So that's x. Wait, I'm coming. Right? So now this is the L2. So now it's not so obvious that this would disappear to destroy when x is 3 or 5, right? So now we can test it out here to see what will actually happen when we evaluate at 3. So let's say we evaluate at 3 now. That would be what? 3 square. I put jumping steps. Right? What's 3 square?
9,
24.
24.
Will this work? I don't know.
Yes.
What's 9 minus 24 minus 15? Plus 15, right?
Yeah. 0 by 0.
You see? So it kills itself once it sees a 3. And it also kills itself once it sees a 5. So let's do that. 5 squared. Right? 25 minus what? Then 25 plus 15 is what?
40 minus 40.
So 40 minus 40. You see? Now let's try for the one it's actually looking for, which is 2. So that's what? 2 square. Is it 8? Yeah. Right? Yeah. Right? That's what? Minus 16 plus 15 is what? Minus 1. 4 minus 1 is what? You see?
Yeah.
So the relationship is the same. It's always either a over a, which is this 3 over 3, or 0 over a, which is the one that kills it.
So, quick question. I
Yeah.
want to know the basic formula. I'm coming.
You're breaking my heart.
Not yet. So, you see, the normal quadratic equation, they do have a normal formula that they do follow, right? So, let's say is there not supposed to be a formula?
There's no formula.
There's no formula.
There's a description, there's an algorithm, right? But you should not need that if you understand this.
Somewhere now, right? Is there no starting point? I think it will be much easier if there's a starting point.
What do you mean with starting point? A starting point for?
Like I said now, let's say you are given a set of, let's say quadratic equation, for example. You are given a set of values.
Evaluations of the quadratic polynomial? Or what?
Yes.
Uh-huh.
Yes. You are given a set of values. So we know that, okay, this certain formula that we have to use, or this certain algorithm we have to follow. So I'm like saying that, okay, let's say you give us a question now, and let's do it. So I'm thinking there should be a starting point for the formula that, okay, use this formula, use this algorithm.
This is it, right? You're trying to find the polynomial, right?
Yeah.
So you have 2 points, right? 1, 2, and 2, 4, right? Those are the points. You're trying to find a polynomial that will give you 2 when you evaluate at 1, and will give you 4 when you evaluate at 2, right? Is that part clear? So the problem definition needs to be understood first.
Can you bring another problem definition?
So let's say you had another polynomial. Let's say f of x is equal to 3x plus 2, right?
Yeah.
This is a polynomial. This coefficient form representation of this polynomial.
Okay, so like this is the question.
It's not a question. Stop. This is not exam. Yeah. don't. This is. It's not. Don't stop. Yeah, I get it.
Yeah.
But don't optimize for trying to pass an exam or trying to pass a test, or don't optimize for that. Optimize for understanding, like core understanding. So this is the problem statement. Now I'm going to go back now. The goal is that there's a polynomial, right? A polynomial can be represented in 2 ways. Coefficient form. Do you know why this is called the coefficient form? Because it has like variables, and every variable has a coefficient, right? So the coefficient for x is 3, and the coefficient for x to the power of 0 is 2, right? So this is the coefficient form representation of a polynomial, of a univariate polynomial. Then there's another way to represent it, which is the evaluation form. So the evaluation form is more like you don't have the equation of the polynomial, but you have points that are on the polynomial. Okay? And we already told you that there's a minimum amount of points that you need, right? In this case, what's the degree of this polynomial? 1. No, it's from Mitch. What's the degree of this polynomial?
Of this polynomial?
Yes.
1.
1. So how many points do you need to describe this polynomial fully? D plus 1. You need D plus 1 point.
D plus 1 point.
Yes.
So 3 plus another one.
Plus 1. So you need 2 points.
Yeah.
So what I'm now saying is that if you plot this thing on a graph and you pick 2 random points from it, that is another way to rewrite this polynomial. Okay? So that's like, let's now evaluate it at 2 points, right? So let's choose 4 and 6, for example. So f of 4 is what? No, for Mitch. F of 4 is what?
F of 4.
Yes.
I don't know.
So you replace x with 4.
Okay.
So what would that be?
I replace x with 4.
Yeah.
So 3 times
4. That's 12.
Yeah.
Then 12 plus 2 is what?
12 plus 2 is 14.
Yes. So f of 4 is 14, right? So this is one point that exists on this line. Okay? Then let's use f of 6. So that's what? 3 times 6.
Yes, 3 times 6.
That's 18, right?
20.
That's 18. 3 times 6 is 18, then 18 plus 2 is 20.
Okay, yeah.
So these are 2 points that exist on this line.
Yeah.
So we can write this polynomial in 2 ways now. We can write it like this, 3x plus 2. Cool. But we can also write it like this. 4 will give you 14, and 6 will give you 20. Do you understand? What's the problem?
So that's why you need to write that this is the final result.
So these two things I've written is the same way of writing the same. Like they're equal. They're the same way. They are like 2 ways of writing the same thing. You get? You get that? So what I'm saying now is that from that one, you can get back this one, and from this one, you can get back down. So the way you get down from this is by evaluating this at 4 and evaluating this at 6, right? Once you do that, you can go back to that one. But then in order for you to go from here to here, that's what we're doing right now, the interpolation. So Lagrange interpolation. So the problem statement is this. Given that, get this. Do you understand?
It's not like you have to do that divide stuff.
Yes. So then the question now is that, okay, how do you get this from this, right? So we now look at the behavior at the top. We want that whatever we get, if we evaluate at 4, we should get 14. And if we evaluate at 6, we should get 20. So if you now think about that, you now see that there's a selection process here. When you see 4, give me 14. And when you see 6, give me 20. So that means that 14 times something. So you're looking for something that is looking for a 4, right? 14 times L4 of x. Then plus 20 times L what? L6. So now this one is looking for a 4, and this one is looking for a 6. Okay?
This is for getting.
We're trying to get back to this one here, 3x plus 2. Yes, using Lagrange. So this is the Lagrange process. Yes. Yes. So this entire thing here, this is the Lagrange kind of, right? But I hid the messiness of the L's.
Let's say without the values, what is the formula without the values?
What do you-
adding those 6 for, let's say the normal basic formula.
Okay. I'm now going to write an equation that is
Yes, I think that's what I'm trying.
this is worse.
Because right now I keep understanding from okay, values.
Yeah. I have no idea. I'm doing it now full algebra, right? You can see this now, right?
Okay, this is.
Wow.
So I'm not done. So what you now want to do is you want to come up with a function, right? F of. Wait now. I'm not done it yet. So it's basically like the output, which is f of a1. Are you following?
Yeah.
Right?
Yes.
right? Okay, then you can now compress it like so here.
Where L is.
Yes. So I'll just write it like this is Lagrange basis technically, but then you can also still write that as like an expression. I'm coming. LAI of x is equal to. So now this is a product, right? So the product from so it's x minus the top is x minus something, and then the bottom is also that thing minus something. But now instead of using this, you now use AI minus that thing. Then we'll call that thing I in the interpolating set. So let's just assume that the interpolating set is called I. So I of I, and then this one is I of I or something like this. There are multiple ways you can do this. Yeah, I could use J also.
This is hard.
So no, it's not about easy on hard. This is just like it's the same idea. There are different ways of communicating the same information. Right? It's just information.
Like this now, can you like give us that whole values equation? Now use this stuff.
It's exactly the same thing I'm doing up there. This is just like a succinct way to describe what I'm doing. But the procedure is what matters. And understanding why we are taking each step is what matters. Do you get? This is not complete though. I'm supposed to exclude where I is not equal to J or something like this. This is not precise. We're not proving anything. Huh? But yeah. But the important thing now is like okay, so does it make sense? It makes more sense. It makes more sense, okay. No problem. So let's now do this too. Oh, we have already done it, right? So it was always A over A or 0 over A. So everybody knows how to construct the L functions now, right? Something that can pick appropriate values. Make sense?
Yes.
So now let's use this to now construct like the original polynomial back, right? So the 2x that we started with initially.
So is it possible for us instead of starting for one out of those three, now we put two?
At once?
Yeah.
So we don't need that. But I think that should be possible too, right? So we just have to think about it. You're saying that we have a set now, right? So like 2, 3, and 5. Then you want what?
Like when I put two.
Or if
Yeah.
you put 2, it should give you 1.
Yeah.
And if you put 3, it should give you 1 also.
Yeah.
But if you put 5, it should give you 0. How do you do that? I know x minus 5 has to be at the top, right? This is not useful. Like not I don't say it's not useful. It's not useful for what we are doing. But I'm just like it might be. These are the reasoning. Like when you are doing stuff like this, you will now come up with like, oh, is this possible? And then you now explore and see if. So if you just learn Lagrange by memorization now, if you stumble on that question, there's no way you can go forward because you didn't understand the intuition behind like how we came up with that structure. But now we might be able to play with it a bit and see if there's a way to come up with that. So I'm guessing that x minus 5 is going to be at the top, right? Because you see 5, you want it to turn to 0. So that's 0 by this thing. So the question now is like, is there a way that we can have it that when there's a 2, it will be a 1, and when there is a 3, it will also be a 1? That's the question. I think there should be a way. So what I'm thinking now is like, you do x minus 2 here also. Then you now do, so this one now, if it is a 2 or a 5, it will turn to 0, right? So it is looking for 3.
That's a flip of what we originally according to this question.
Yeah, it's trying to find 2 and 3. Not just 1. No, we're only trying to find 1. But now I'm trying to find 2 at once. Yeah. So I'm trying to see if there's a way to do it. So what I'm thinking of doing is I'm thinking of splitting it into 2 equations. So this one is looking for 3 specifically. So if there's a 3 there, it's going to be what? 3 minus 5, right? And 3 minus 2, right? Then I cannot do this again. So this will now be x minus 5, but this time it will be x minus 3. So 2 minus 5 and 2 minus 3. Do you get this now? So if the 5, in both sides, it will be 0. So when you do 0 plus 0, it will still be 0. Now, if it's a 2, in the first part, it will be 0. But that part will be 1. So it's selected for it. And if you're looking for a 3, then this part will be 1, and that part will be 0. So that solves what you're asking for. But that's only because I had the intuition of how Lagrange works. I don't know how you can use this, though. There might be a way to actually use this for something interesting. But can anybody now think of a way to do right now we're doing binary, right? 1 and 0. It's possible to do 2 and 0, right?
Yeah.
It should be, right?
Yeah.
You don't want it to output 1 and 0. You can output 2 and 0. How will you do that?
The numerator will be 2a, the denominator will be a for the first part, and the other one, the numerator will be 0, the denominator will be a. So you make all the equation equate to give you 2a over a, so that you can get an output of 2 instead of 1.
Okay, so what you're saying now is 2a over a, right? This is our goal now, rather than what we had before, which was a over a. Yes. And how do you do this? You just put 2 in the numerator. Yes. So 2 times whatever the numerator is. You always put 2 times whatever the numerator is. So if there's a 0, then 2 times 0 will be 0. So it's always 0 over a and 2a over a. So this is the flexibility that you have with understanding. Does it make sense?
Yes.
But what we care about is just a over a and 0 over a. Let's do a full thing. Let's try and do maybe 2 examples before 12. Then we'll just take a break. Then we'll come back. Oh, you want to write something?
Yeah.
This one? I don't write it all. So there's a book called Proofs, Argument, and Zero Knowledge. Yeah? So by Justin Taylor, yeah. So what I wrote, I don't think it's precise enough. That's why I said you shouldn't write it. So, huh? Yo. Okay. Alright, we'll finish quick. Then I'll charge. Thanks. So this is the product. This is the one I felt I didn't write correctly. But this is the one I felt I didn't write correctly. But then the other one is correct. So that's this one here. But let me write that. I'll send it back. So I'll share this notes too.
Okay, on Telegram.
Yes, on Telegram. I'll share the notes on Telegram.
At the top.
Which one?
That one, no. Yeah, the bottom at the bottom. Is it like an official formula?
There's no official formula. But yes, technically. Yes, technically. It expresses Lagrange. Yes, it expresses Lagrange. No, there are different learning styles, so I'll make sure that I cater to you too. Okay, guys, let's try a full example. Let's try 2 full examples, then we'll take a break. So 2x, right? Yeah, that's what I'm starting the first example now. 2x, right? Then I'll go back to the other one. Yes, 2x plus something. So now 2x, this is the polynomial, right? F of x. This is the coefficient form representation of this polynomial. Then we're going to get 2 arbitrary points from it. So let's evaluate at 2. That's 2, 4. And let's evaluate at what? 4. That's 4, 8. So these are the 2 points that we have. Now we want to get back 2x, right? So the output 4 should only show up when the input is 2, right? So we need something that can select for 2. And then the other one, the output 8 should only show up when the input is 4. Make sense? Yeah. So all we need to do is now get these 2 functions, right? So let's first do L2. What's the interpolating set? 2 and 4. So the interpolation says 2 and 4. Now what we want to do is, if it says 2, 1. If it doesn't say 2, so L2 of x. So what are we trying to kill? 4, right?
Yeah.
So top is going to be x minus 4, right? And that's all, because it's just 2 points. But then when it is 2, the top will be what? 2 minus 4. So we need to divide by 2 minus 4. So this is 2 minus 4. If we simplify this, what is that? I think I will simplify it further by just taking the minus up. So this is fine for now. So we have L2 of x, right? So that will go there. Now let's get L4 of x. So we're trying to destroy 2. But then when we evaluate with 4, that will be what? 4 minus 2, right? So that's what? X minus 2 over 2. Good? Now we replace it back in there. So the final formula f of x is going to be equal to 4 times, what is L2 of x?
4 minus x over 2.
Right? Technically this can cancel out, right? So that will just be, okay, let me not hide steps, just in case if someone retroactively says this. Then plus what? Right? So in the next step I'm going to cancel out now. So that's 2 plus what? Cool. Now we multiply out. So 2 times 4 is 8. 8 cancels out. Then we're left with what? 4x. What is 4x minus 2x? You see it. So we're able to get back. Does it make sense?
Yeah.
Does anybody not understand it? Everybody understands it? Wow. Okay. So let's do another one, just one more. I'll send the notes. But you can take a picture if you want, but I'll send the notes.
One more.
Yeah, one more. Then we'll take a break. Then we'll come back and start thinking about implementations. Yeah.
That last one, we only used the first 2 points.
Yeah, because it's a degree 1 polynomial, right? 2x. And that means that it only needs 2 points to uniquely describe it. So that's why we only needed an interpolating set of length 2. But technically, you could still do Lagrange interpolation with as many points as you want. You still get 2x.
The 2 points are x and y.
No. xy, then x1, y1, x2, y2. Yes. So there are 2 x's and there are 2 y's corresponding. Does that make sense?
Yes.
Okay. My battery was on there. Let's do something more. I don't want something too complex. Oh, yes, we see. Thanks. Yeah, I wanted to do like a quadratic, but I feel like. Yeah. Yeah, thanks. I feel like it might be complicated. Like we'll have to do a lot of manipulation, but let's just do it. 3x squared plus, so that's a constant. Yes. So let's say we had 3x squared. So, what is the degree of this? 2. So how many points do we need?
3.
So let's just use 0, 1, 2. That's actually what we use. So you know the way I've been writing the x comma y as a tuple, right? Like this. There's an assumption that you can make. If you're always using 0, 1, 2, then the index of the array is basically the x value. So you can collapse it down to, so like in this case, now let's do the 0, 1, 2. You can write it like this, like 0 is 0, right? 1 is 2, and 2 is 4. You could write it, but we could collapse it down in one array. So rather than using a tuple, an array of tuples, you could use just like 0, 2, and 4. So you instantly know that the index of the array is the x value. You get? So 0, 0, 1, 2, 2, 4. So these are some implementation-ish details that one can use. So after the break, we'll come back and just like brainstorm on how one might implement this. What time does the other class start?
4 or 5.
4.
4.
Okay. Might take maybe like a 30-minute break just to get our brain settled a bit. So that's if already at. We need 3 points because they're degree 2. So if I rate at 0, what are we going to get?
5.
If I rate at 1, what are we going to get? 8. If I rate at 2, what are we going to get? 4, right? 2 squared 4, 4 times 3, 13, 12 plus 5, 17. Cool. So these are our y values. What is our interpolating set?
0 and
So I evaluated it at 0 to get 5. So imagine x is 0. So you could think of this as like 0, 5, 1, 8, and 2, 17. But I'm just writing that because it's simpler. So what's the interpolated set? 0, 1, 2. Okay, so now the actual function is f of x is equal to, what's the first output? 5 times what? What is it selecting for? L0 of x. Plus what? So all we need to do is just construct those functions, put it back in there, simplify, and the hope is that we get back 3x squared plus 5, as long as we don't make a mistake. Okay. So interpolating set is what? 0, 1, 2, right? So we need something that selects for 0 from this. What's that going to be? Yes? So what is under? Okay. Simplifying. True. Let me just go straight. So x times x is x squared. Divided by what? Minus 1 minus 2, which is 2. So let's simplify fully. So this is L0. So you can already start seeing that it has a square inside. That's because of the other one has like this. Now let's do L1. So I'm selecting for 1 now. So that's x minus what? So you know this x minus 0 is x. So x will just distribute. So that's x squared minus 2x. Divided by what? 1 times minus 1, right? That's minus 1. So we can flip it, alright? Does this make sense? Then let's do the last one. This is going to be crazy though. X minus 0. Collapses 2, right? So x squared minus x. What's this? 2. So cool, we now have the 3. We just replace it into the thing. So that was what? 5 times brah. Let me just simplify this. Huh?
You should make that one but so L1
And so I can remove it already. Yeah, but don't worry. Wow. I get what you mean though. So I can distribute this in right now, right? I get what you mean though. I think I should don't worry, let's just do this. Then plus what?
8.
This is why you have programming languages on computers, so that you don't have to do this by hand anymore. Is that 17? So let's just do this. Alright? So this is 5x squared minus 15x plus 10. No, 16 times 2, right? That's 2.
Yeah.
16x squared.
Minus 16x.
So hopefully things start to like cancel out. So let's just collect all the x squares. So that's what?
5x squared minus 16x squared.
17x
Plus
squared.
17x squared.
That's alright.
Minus 15x.
Then minus 15x.
Minus 17x. Plus 10.
Right?
Yeah.
So let's do the x squared. What is 5 minus 16?
6x squared.
So I'm already seeing where the 2 will come in. So what's the x one? Is 0? So I don't write anything then, plus 10 over 2, right? Then we can divide both. Does it make sense? Perfect. So Lagrange interpolation is what we use to go back. Yes. It's not fast. It's not very fast. So there are different ways that there's a very naive way to implement this that runs in O of n square. I think there's a better way. I think it's always going to be O of n square. There's always going to be O of n square. There's always going to be O of n square. So there are multiple ways to implement it. Then there's now another algorithm, which is called the FFT. FFT. Fast Fourier transforms, but applied to polynomials. So in our case now, finite fields is actually called entity, but they're exactly the same algorithm. The only difference between this and this is that fast Fourier transforms.
Fast Fourier transform.
Yes. Why this one is number theoretic transform. But it's just the only difference between them is just one uses finite fields, one doesn't care. But the algorithm is the rapid. Finite fields. Do you know what finite field is? Yeah. So like a set of numbers. I'm not giving the precise definition, but you have like a finite set of numbers. You know how numbers normally go from like 0, 1, 2 all the way.
Is it field as in mass?
Like math field, yeah.
Field.
Yes, field. FIELD.
Vector space.
Technically, no, E is like yes, like a field with all those properties, like the close, yeah, exactly. So that's what we use here, like in cryptography, is just field. We don't use real numbers and all those things. So, but the algorithm is the same. So this algorithm is much faster than the Lagrange, and that's the only thing that is basically used in this space. But it does exactly the same thing. Right, so you are going to get back this 3x squared plus 5, and then there's an inverse. Actually, FFT will take you from this to the evaluations. Then IFFT will take you from the evaluations to this, but it's much faster. So if you're interested in playing the game at level 2, I suggest that you try and like understand FFTs yourself and try and implement it. Okay? Well, we'll still teach you. If you want to play it at level 1. So,
So if you like jump from DSP, right? From DSP.
what is signal processing?
Digital signal processing.
Yes.
Is the one.
Yes. It's the same FFT. But you need to look at the videos or materials that try and show you how to do polynomial multiplication. So there's a way to apply it to polynomial multiplication. No, you don't need to. You don't need to. It's more. You could do that, but it's harder to understand. It's not over time. We don't care about that yet. Yeah, we don't care about that yet. But it's exactly the same algorithm. So, no, FFT. This algorithm, the FFT algorithm, is used in signal processing. Yeah, but then you can also use it for this. Yeah, it's a divide and conquer algorithm.
If we add extra data points, now we can get a higher degree, right?
So if we add extra data points that are also on this 3x, we will always get back this 3x squared plus 5. But if we add extra data points that are not on this, then you'll not get a new polynomial. Yeah.
With a higher degree.
Yes, most likely with that. Yeah, with a higher degree. I'm trying. So that makes sense now. Any questions? Alright. Let's go for a break now. We'll come back by 12:45. 45. Yeah.
Oh, Allah.